Okay, let's get started. So just before we start, I did send you all this information that's on this slide already in the email that you got this morning. The most important thing here is this HackMD link because it contains all that information and also gives you the opportunity to add notes to that page as well. Actually, speaking of which, I might just open up the permission so you don't need to log in to do that. Just let me do that. So I'm just going to change the permissions here so that anybody can edit. Everyone. Okay, that should be possible now. So if you go to that link, you can add some notes if you feel that might be useful to other people at the end of that link. So what we have for the tutorial today is, in terms of helping you with the hands-on, is we have a small Linux cluster. Alma Linux is the operating system, and that's in Azure, so it's in the cloud. That I brought that up yesterday, and it'll be here until the end of the tutorial. So I'll probably shut it down pretty soon afterwards, like around 6 o'clock this evening. To use that system, you need to create an account. The link is here in the slides, but it's also on that HackMD as well, so you can just use that. There's a couple of people here help me today, and they'll approve your account, and then you should be able to sign up to log on to the system. We're approving them right now, and then just remember to keep note of your username and your password that you have there, because the reset password link doesn't work. So you need to remember those. And if you have a problem, then the guys should be able to help you out in the Slack channel. Communication. So if you have like general questions, the Slack channel is probably the best place to ask them, because there's lots of people in there who most likely know the answer already. If you have something that's specific to the tutorial here, feel free to raise your hand and ask about it. This is the place to do it. If you raise your hand, then either myself or the guys here who are helping me can unmute you then, so you can ask the question. To access the cluster that we're going to use, you can do that two ways. You can just use SSH. So remember in that username that you have, and then the name of the cluster then is just cluster.eec.science. Or you can do that through your browser, right? So basically that URL that's there. So cluster.eec.science again. So I'm going to do that now, just to start an account for my to start a job. Did I already log on? No, I didn't. Here we go. Okay, so if you go to cluster.eec.science, I can do it again. You'll get jump to this Jupyter Hub interface, and with your username and your password, then you can sign in here. You're given these options about what you want to run. So here I've already increased my core count to 4, and because I'm the one who's going to be doing the things. 2 is a good option here for you. I've given myself, you could use 4. I don't know how many people we have in the system. We have like a total of 160 cores in this cluster, or a little bit more actually. So you could use 4 cores. Depends on how many people we have. We may run out of resources if you use more. You can use the login node directly as well. So if you use SSH, you'll jump onto the login node. But if you use the Jupyter Hub option, you'll actually be running on the nodes themselves. So you can increase that to 4, and I have 8. I'm going to make a job time of, the default is 1. I've already changed that to 6. It's too much, but it's don't want to be kicked off in the middle of the tutorial, right? So we just press start then, and then it'll jump me straight into an environment. Yours will look slightly different because I've customized mine, so you'll be able to read my text very easily. So I'm just going to start a terminal there by clicking on the terminal button, and we'll get rid of the files for them. Okay, so so now you're logged onto this cluster, and you can also do the same thing by SSH, just the simple SSH command, but basically we just want access to the cluster from here. Okay, so let's get started. So I'm here today together, it's a collaboration, this tutorial with CASTIEL 2. But I want to do an introduction to the European Environment for Scientific Software Installations. The acronym is gamed a little bit, right? So the way we pronounce that is EESSI. so the EESSI environment. My name is Alan Akash. I'm the technical manager in the Multi-Scale Center of Excellence. I work at the University of Barcelona, and I'm also affiliated to CCAM, which is a scientific organization that's been around for more than 50 years. I wanted to start by just talking a little bit about the changes that are happening in scientific computing. So in general, with the openness that we have in research these days, there's an explosion of scientific software that's available. And so if you think about things like bioinformatics and AI and other areas, right, there's a massive explosion in the applications that scientists are using. There's also an increased interest in cloud computing, right? Because like people may have access to HPC resources, but there's typically a queue there, right? And so maybe they need more flexibility in that, or maybe they have workflows that require different capabilities, and cloud is a place that potentially they can find these things. The other thing is there's an increased variety of processor and microarchitectures out there. So, you know, beyond the typical Intel and AMD, ARM is already there in the space, right? We already see that on very large systems like Fugaku. We'll see that in Jupyter in 2024. And so that's the big exascale system that's coming to Jülich next year. And then we have RISC-V, right? So there's a lot of money being pumped in Europe and also in China as well, and other places into RISC-V as an architecture that could be used for large-scale systems. So that's also coming, or even arriving, right, at the moment. In contrast to that, HPC sites, they've always had limited person power, and that's still limited, right? But the amount of things that they're expected to do is unfortunately growing, right? So support teams are very busy. So Kenneth Hoste is from the University of Ghent, and he gave us some figures about the number of software installation requests that they've gotten over the last 5 years or so, 5 or 6 years. And you can see in 2022 there was a big bump already, so you're up beyond 350 software requests, right, in a single year. And already in the first 9 months of 2023, it's probably going to reach the same kinds of levels. So that's a lot of software requests that are coming in that support teams are being asked to report, and that's not unique. So University of Ghent is like a university level system, like part of the national infrastructure in Belgium, but the kind of requests that they're getting is probably quite common, right? And the level of requests that they're getting is quite common as well, I would expect. In our case, what do we care about? So we're dealing with scientific software, and we're dealing with high performance computing systems. So we care about optimization. We care about the performance of the applications that we use on these systems. So the software that's used should be optimized for the system where it's going to run. And if you're talking about portability of applications, the easiest way to get portability is to not specialize the instructions that you use. So make a more generic version of your executable that you can use on multiple systems, right? But that has an impact on performance. And typically for scientific software where you really care about that performance, it can be quite significant. So the graph here is giving you an example of that, which is for GROMACS. We're like an older version of GROMACS now, but the principle is the same today as when the graph was generated. So basically with GROMACS you can kind of measure performance in the number of nanoseconds you can simulate per day. So higher is better here. And this was a Cascade Lake system, and it had 36 cores, and we're just looking at the simulated seconds per day. You can see that if you have what you might call a portable binary, which is say like something like you might get from your operating system, and that's down here, that performance say is at 1.0 nanoseconds per day. But if we actually compile the code for different instruction sets, which is basically equivalent to compiling for different, or kind of like you could draw some equivalence to compiling for different architectures, you can see that you can increase that performance by up to 70% by compiling for the architecture that you actually have available to you. So for the instruction set that you actually have available to your CPU. So what does that mean? That means basically compiling for the hardware that's available to you, and you can get an increase in performance by up to 70%. But that comes at the cost of having to do that compilation, right? So having to compile for the architecture you actually have access to. So in some sense, you could say the cost of there's two kinds of cost. There's the cost for me for compiling my application, and then, but if I want portability, I could compile lower down, but that comes at the cost of performance, which everybody pays, not just me. So the European Environment for Scientific Software Installations, what that is in a nutshell then, the idea behind it is that we want to create a shared repository of optimized scientific software installations. So we want to give you that portability, but we want to make sure that you still have an optimized software stack. We want to avoid this duplication of work that necessarily happens right now between different sites by collaborating together on that shared software stack. And we want to provide a uniform way of delivering that software to users, regardless of the system they use. And when I say regardless here, I mean, it doesn't, regardless of whether that might be their laptop, a virtual machine they have access to, the cloud, an HPC resource, a server, whatever it is, the system that they have access to, that their way of interacting with that software stack remains the same. And the software that they're available to remains the same as well. This should work on any Linux OS, and it also actually works on the Windows subsystem for Linux as well. We have looked into the past on supporting this in Mac OS, and it is something we will come back to. But right now it doesn't work on Mac OS, but it could. In principle, it could still work. It works on laptops, personal workstations, and to HPC clusters in the cloud. And we'll see some of that today. We have support there already for a range of different CPUs. We've tested things on different interconnects. We are working currently on GPU support that is in principle exists, and it's currently under code review for incorporation before the end of the year for NVIDIA GPUs. And then, so we're looking at lots of different hardware with the EESSI software stack as well. And our focus is on performance, obviously, but automating things, automating as much of what we can for the EESSI software stack. We want to test things, so we don't just make things available, we actually test them before we make available. That includes the test suites that come with application software, but it can also go beyond that and include scalability and performance checking for software before we ship it. And the idea is that we want to collaborate. We want to collaborate on the software stack itself, but we also want to collaborate with the application developers to make sure that we're shipping the best version of their application to the end user community. At the bottom here, there's a couple of links that might be useful. So the main EESSI website and also the documentation repository for the documentation site for EESSI as well. So our major goals are to avoid this duplicate work. So to make sure that not just for the HPC support teams, but also for the researchers themselves, right? Wherever they need to have their software available to them. There are tools that already help in this space, right? So EasyBuild, so the EESSI project has kind of grown from people who have contributed a lot to EasyBuild in the past. But there are other tools like SPAC and beyond as well. There are more tools that help in this space. But in general, we feel that at this point, they're not sufficient, right? That we need to go beyond just sharing just build recipes and methods for installing software, but we can actually, there's no technical restriction to us providing the actual software stack itself, right? So the users don't need to become familiar with the tools that we use underneath. They just need to get access to their software and use it. We want to provide a truly uniform software stack. So that means that the ultimate goal is to get the same exact software environment available everywhere, regardless of what architecture you have access to. And we don't want to sacrifice performance just to give us mobility. And this is still something that's typically done with containers or with the Conda environments or something like that. So there is typically a performance sacrifice when you talk about portability of these kinds of environments. We also want to facilitate HPC training. We want to bring HPC to the masses, right, and remove this kind of to make HPC more accessible to the ever-growing communities that want to use these kinds of resources. And then we want to make it easier for people to develop and distribute scientific software as well, among other things. So to give you a high-level overview of what the EESSI project looks like, so basically on the bottom level, you're always going to have your host operating system, whatever that might be, and that's going to provide all the ways of using the hardware that you have, right? So it's going to provide the drivers that you need to work with your network and your GPU or whatever accelerator you might have access to. It's also going to provide things like your resource manager. What we put on top of that is our own file system layer, and that's basically a web-based file system that we use to distribute the software stack. Inside that file system, then we create a compatibility layer. And that's effectively like an operating system that sits on top of the host operating system. It kind of works the same way as a container, except you don't need a container runtime environment. And then on top of those, we have the software layer. So the software layer is where we have all the optimized applications and all the dependencies for all the applications that people might want to use. And then we have testing on the left-hand side here. We have testing across all the range of the 3 layers, right, to make sure that everything is working correctly. This is all facilitated by lots of open source software. So on the bottom, we have things that we currently support. So in terms of the hardware, the families of CPUs that we support, so Intel, AMD, and ARM. We have supported Power in the past, but there's not a lot of motivation to do that anymore. So we've actually removed support for Power. The tools that we use are CPMFS for the distribution layer. I'll talk a little bit more about these tools later. Gen 2 to do Gen 2 prefix to do the compatibility layer, and then we use EasyBuild and EasyBuild to do the software installations. LMod, which provides the user interface, so that's the module environment, and ArcSpec is the tool that we use to automatically detect what architecture you're working on. So these are lots of names I've dropped there. But the important thing is what you get in the end is you're getting streaming of scientific software. So the same way that you interact with services like Spotify or Netflix or any of those kind of streaming platforms, you basically have a catalog of software that's available to you. You select what you want to use, and then when you start using it, the files that you actually need to make that application work, they're streamed in transparently in the background. So they appear to you as if they're on the file system that you have access to, but they're not actually there until you start using them. So you can draw an awful lot of parallels to how streaming services work. And with that, I want to start with a demo. So a demo that brings us straight from nothing, basically, from an empty virtual machine. I'm going to use an operating system that I don't know if many of you have probably used in the past. So Amazon Linux, it's a custom Linux operating system that they use in AWS. We're going to use exotic, inverted commas, exotic hardware. We're going to use an ARM instance in this case as our hardware. And this system doesn't have any CERN VMFS installed. It doesn't have EESSI available, and we're going to start that from scratch. It does require the admin rights to be able to do the installations, because we need sudo to be able to install extra packages. And then we're going to set up the EESSI environment by sourcing a particular script, and then we're going to run some demos from a demo repository. Okay, so let's get started. So, the first thing we need to do is create an instance on AWS. For those of you who have never done this, this is what it's actually like to use cloud environments, or depends on how you use it, but one of the most simple ways of using a cloud environment. It's already selected Amazon Linux for me. I want to change the architecture because I'm interested in using ARM. Then you can select what kind of instance type that you like. I want a little bit of CPUs, not too many. I'm going to choose 8 CPUs here. So that's a particular instance type. And obviously the different instance types come with different prices. So this one is about 30 US cents an hour. And then I'm going to select the key the SSH key that I'm going to use to log onto the system. That's the one that I have stored already in AWS. So I can launch that instance. And then very quickly, the instance is launched, and it'll give me information about how I connect to that instance. So I will copy that command from there, go back to my shell. And this is just a demo. You won't be doing any of this now. I just want to show you how it works. Okay, so we're logged onto. So I just spun up a virtual machine in AWS, and now I've logged onto that system. There's nothing available here, very, very little, not even Git. right? So first thing I need to do is sudo yum install -y. I need git installed. Okay, so we got git installed now, and now I want to clone a particular repository. And so that's the demo, the EC demo repository. The link for this is given in the notes already, but if anyone wants to add additional notes there, they're free to do it. So that's the repository. I need to clone it. Git clone. Now we can see we've got the demo repository available locally. Let's go inside. So you can see there are a couple of different directories here that have demonstrations for different applications. Bioconductor, GROMACS, OpenFOAM, and TensorFlow are the end user applications that are available here. There's also a scripts directory, and inside the scripts directory is actually what I need to install CVMFS and EESSI. That's the first script that's available over here. We can look inside. It's a bit hard to. There are a couple of different. So this script supports different operating systems, including AWS. So basically, has a lot of logic into that side to figure out which operating system you're using, and then it does various things based on that. So whether you're using RPMs, so like Red Hat based systems, or whether you're using Debian based systems, you can figure that out. So we can just run that script, and it will go away and install CVMFS for us. And then it will install the configuration repository for EESSI. Doesn't really matter what that means right now. We'll talk a little bit more about that later. But basically, we're not installing the software here. We're not installing TensorFlow. We're not installing Bioconductor or any of the other applications right now. All we're installing is CVMFS. And it takes a few seconds for this to finish, but not too long, about 20 seconds, I think, or so. There we go. So the process is complete, and now we have, because CVMFS is a file system layer, it appears in a very particular location /CVMFS, and if we look inside, there's nothing there. So a new location on our file system has been created. There seems to be nothing inside, but that's because the repositories, so the things that are shipped via CVMFS, are auto-mounted, so they don't appear until you actually look inside. So one of the ones that we're going to need for the examples is the pilot repository. So pilot.ec-hpc.org. If we just even list it there, you'll see that something happens, right? And all of a sudden, I've got additional stuff available to me. The production one that we just released for EESSI is called software.ec.io. That also has just been mounted, right? So, and then we can see, so we now have these new directories in here. We have the configuration repository that's coming from CERN. That's so EESSI is shipped by default via that configuration repository, and that's what gives us software.ec.io. And then we have the old, what's kind of, now you could talk about it as the old stuff we had when we were testing things. So that's the pilot, and we're going to use the pilot one actually for the demos that we're going to do right now. So now we have at least EESSI is available via CVMFS, but nothing is configured in our environment now. So if we try and do like a typical module avail, which is typically how you interact with HPC systems to use the module environment, you'll see that this will not work, and the command is not available locally. What we need to do is source a particular script. So if we go to the pilot, and then there's a certain directory, we can just do latest, that's okay. And we go to an initialization directory, and we're in bash, so we'll just initialize bash. You can see another number of things have happened, right? So first it says, oh yes, I found this version. It's a kind of an old version now, but it doesn't matter. It'll work just fine for the demos that we're going to run. It runs the argspec command and figures out what architecture we have available to us. So we've got Graviton 2. So then it chooses an appropriate subdirectory for the software. So it's giving us software that's optimized for the Graviton 2. Then it configures LMOD, so configures an environment module tool, and then adds a certain location to the module path. So adds a certain software. And then if we run that module command that we just ran before, and module avail, we'll see that there's a lot more software all of a sudden available to us. So a big long list of things, right? And lots of extensions as well. And this means then that now we have let's see where we are. So now we have the capability to run some of the examples. Well, let's start with, well, okay, let's go for the GROMACS example. So in here, we've got an example that we can run. So this is run.sh. Let's have a look at what's inside. It's going to load a particular module, a particular GROMACS version. It's going to download a test case for GROMACS if it's not already available. The same with, and unpack that if it hasn't already been unpacked. And then it's going to run a GROMACS executable, right, with that test case. So we haven't installed GROMACS yet in the system, but if we run that script, we did see, so if we do module avail, GROMACS, we can see that there are actually two versions of GROMACS available, and one of them is the one that we require. So if we already just run that script, it seems almost instantaneous, but GROMACS is already running on the system. So we never installed GROMACS, but the files, once we had CVMFS available, the files became available. And then once we tried to load the GROMACS executable, CVMFS goes away and pulls in what we require to actually start running. And because of the location of where this virtual machine is running, that happens really, really quickly. And so we can see for GROMACS now, we're already halfway through the cycle. I think it takes about 20 or 30 seconds for this example to run. So we might as well wait until the end. Hopefully it won't be too much longer. The other examples are a little bit faster. And there we go. Okay, so we just ran that GROMACS executable in just a few seconds. So now if we go, there are other examples here. So I don't know what the domains of people are on the call, but they're so say bioinformatics typically has lots and lots of software available to it. Bioconductor is a package that kind of that packages a lot of that software into a single bundle. So here we can see, what does the bioconductor run script do? There's a script in this directory, an R script, that has lots of dependencies, and we're going to run that R script. So we're going to pull in lots of software that's required to run this bioconductor package and run this test. So again, we just run that, and immediately it looks like it's as if it was already available on the system. It starts running that software. And this one takes about 20 seconds or so, I think, to run. There we go. Oh yeah, it did have to download some things actually as well as part of that script, I believe. There we go. It's pulling in packages all the time while it's running. So there we go. The workload is finished. I have no idea what that workload means, but we can see that the software is working correctly and as expected. I'll do one more example, which, let me see, TensorFlow, right? So TensorFlow is a difficult one to get installed, and we can look at the run script for this one. So any of you who use TensorFlow know that it's actually quite a large install. So it's about a gigabyte, probably. Depends actually on the architecture, how big it is. It can be anywhere between like a gigabyte and a few gigabytes to load that software, with lots and lots and lots of files. So we're going to load the TensorFlow module, and then we're going to just run a TensorFlow script. So again, as before, we just run that example. And TensorFlow, if anyone have used TensorFlow, you know that in general, it takes time for TensorFlow to run, to load up. So typically a few seconds. And in this case, we're immediately running that TensorFlow script. And that's it. So that's actually the quickest example that I have, even though it's probably the largest software package of what I've just loaded. Okay, so that's it. So on this AWS system, then we installed the CVMFS packages. There was a configuration package for EESSI as well that we installed, which was kind of hidden away in that script, but that's basically what we used. So to configure the access via CVMFS to EESSI. It also, inside that script, at the end of that script, it generates a client configuration. So basically in that client configuration, one of the most important things that's in there is that you're deciding on how big the cache is that CVMFS can use. What that means is how much software is how much space is CVMFS allowed use on the system to store software. And then basically it uses cache principles then to kick out packages that it hasn't used in a while. So its most recent use are the ones that are kept in the cache. For production usage, especially at large scale, there's a few other steps that you would probably want to do if you were going to use EESSI and CVMFS. So you'd want to use things like, we'll come to this later on, explaining what this is. And also yesterday, there was actually a tutorial on CVMFS that EESSI and multi-scale gave, and so there's actually a quite extensive tutorial available, that's actually available on YouTube, I believe, already, about CVMFS. But basically, you want to use things like a squid proxy, so you want to increase the performance and for your local system. You can do that through a number of ways. One of them is a squid proxy. Another one is something called a Stratum 1. We'll come to these things a little bit later. And then in general, of course, it's also recommended to be a good citizen in the network as well. That means like trying to take care of there are a couple of like best practices that you should be implemented when you're trying to use these things at scale. Once CVMFS and the EESSI configuration was available, we were basically good to go. We were able to source a certain script and set up the EESSI environment to load modules and run. Okay, so we could have, well, I didn't actually do this command, but basically you could see the different versions of GROMACS and TensorFlow and OpenFOAM that are available in that environment. One final comment is just that the production version of EESSI is at software.eessi.io, and you can already have a look at that in the environment by sourcing a different location. So it's software.eessi.io, and then the other things that if it's not in the notes, can somebody please put that in the notes as well, if these different locations source different EESSI environments. And the reason I didn't use that now is because all the demos that we have in our demo repository don't actually all work with the production version yet. So that's like a work in progress. And with that, I wanted to give you the opportunity to do a hands-on of running the demos yourself. So basically on the infrastructure that we have available, you you log onto that system, whether it's through SSH or through the web-based interface, so Jupyter Hub. The EESSI is, or CVMFS and configured to use EESSI is already available in the system, but it's not available in your environment yet, right? So you still need to do sourcing, whichever version you want, whether it's the old pilot, the pilot version, or the current production release. The nodes are not that low spec, I suppose, but they have 16 cores or Skylake systems, so and the front end is the same, it's also 16 cores. But the examples are also not very demanding, right? So we've only used we used 8 cores when I was running, but you could use they will run just fine in 4, and they won't take very long. You can run one of the EESSI demos after cloning the GitHub repository for the demo location, and that should be in the notes. It's here. I'll leave it available on the screen as well if you want to just type it out. And yeah. So now you can take a few minutes, so let's say 5 minutes or so, and to give it a try for yourself. And if you have any questions, you can ask. If you have more general questions, now is probably a good time to ask as well. But I'm just going to give you a few minutes to try this on your own. I'll take the opportunity to look through the Slack as well to see where we are. Let's see.
For the people who are trying that hands-on, maybe either in the Zoom chat or in Slack, preferably, let us know if that's been working for you. So we have a few on how people are doing.
Yeah, and if you have any issues, you can raise them on the Slack channel, and if you want to discuss something, you can do that here. You can raise your hand here, and we can discuss it here as well. So for me, I will log out of the system here. Okay. So I have already done the git clone of this location. I have a few other things as well that we'll get to in a while. For me, I'm going to run the demo, and I modified TensorFlow example a little bit, so we could actually run it with the production release of EESSI. And so for my part of the hands-on, I'm going to run the TensorFlow with the production release of EESSI. You can look at what I changed here. So basically, in the version that you clone from GitHub, there'll be a version attached to the TensorFlow, a very particular version. But I'm ignoring that, so I edited this to just load whatever version of TensorFlow is actually available. So we can see if I do module avail, I don't have the EESSI environment initialized yet, so I want a source. And like I said, I'm interested in the production release, so that then versions 2023, and then the initialization directory. I'm initializing bash. Again, we have the same things as before. It says it finds the version, it recognized the hardware that I have available to me, and it's doing things based on that selection of hardware. And then if I do a module avail, again, see I have lots of new software that's all of a sudden visible to me. And we can do module avail, TensorFlow. And you can see TensorFlow version 2.13.0 is available, and there's a couple of module extensions as well, Python module extensions that are those, obviously including the Python TensorFlow. Okay, so then again, as before, I can run the script. And again, TensorFlow always takes a few seconds to load because it brings in a lot of stuff, and is quite large in size as well. So on any system, it takes a few seconds for TensorFlow to start. In this case, I don't have TensorFlow locally, but it's already running, right? So we've got, I think I have four CPUs in my environment right now. So it's taking a little bit longer than the 8 CPU version, but you can see it's progressing rather nicely. Finishes in a few seconds. So the TensorFlow example does work with the TensorFlow demo does work with the production release, but we don't have all the other software that's necessary to run the rest of the demos. So if you are trying the other demos, then you're better off using the pilot environment for that. Yeah, and you may not be able to, so it just was raised there that sourcing the script, unfortunately, is not a reversible. So your environment is if you want to switch between the pilot release and the production release of EESSI, the best way to do that is to open a new terminal. So give yourself a clean terminal when you want to do that, because it doesn't happen cleanly when you try and source one script after the other, unfortunately. That's something we will fix in the near future. So I don't see a lot of traffic in the Slack channel with people having issues. But if you do have them, let us know there. Like I say, I'll give say 2 more minutes for you to try things out. So there was a question in the Slack channel about installing CVMFS. You don't need to install CVMFS. So the prepared environment that I've given you doesn't require you to install CVMFS. It's already available there. So you don't need to run the installation script. And that script requires sudo, and you obviously don't have sudo rights on the cluster where we are, so you won't be able to run the installation script. That script is there for an environment where you would have those kind of rights. So in a cloud environment, potentially in a virtual machine that you have on your own laptop or something like that, or on your own laptop itself. So there is no need to install CVMS. All you're doing is sourcing the locations. You do not need to install CVMS on the cluster. There is a question in the Slack channel about what's the policy for getting software into the production repository, and we will come to that. And that is en route to the presentation. So there's somebody said it wasn't clear exactly what they're expected to do right now. So I can go backwards a little bit, but basically, you log onto the system. So the system, this prepared system that we have available, and if you don't know about, maybe you joined the tutorial late, but it's in the notes, and I sent the link to the notes in the email this morning. So basically, you log onto the shared system somehow, and then you need to source a certain location, and that looks like this. Let's go back here a little bit. So you need to source a particular location. That should be, I believe, in the notes as well, hopefully at this point, about what you need to source. Yes, it is. And then basically you need to clone a certain repository. So that's the demo repository for EESSI. That also should be in the notes, and what you need to do there. And then you just go to one of the demos that's inside. So go into the directory, go into a software subfolder in there. So for example, Gromax, and just run the script that's inside. So there's a script called run.sh, and the idea behind this demo is just to show you how quickly and easy it is to start doing scientific work when you're using EESSI. That's the basic motivation for the demo. Okay, I think that's probably enough time on this. I don't see. Yes, so Richard, so somebody said in the Slack that 2023 didn't work for them. That's right, and those demos are intended for 2021, and we will support them in production repository in the future, and probably in the very near future. The TensorFlow demo does actually work in the production repository. You just need to edit the run script, not to load a particular version of TensorFlow, but all of these will be supported in the future. Okay, so let's keep going. And then if you have any other issues, you can raise them in the Slack, and others are there to help you out. So if you want to keep trying with the demo or to play around with things, you can do that there. You can also use these things anywhere you have access to resources. So you can use Aptainer or Singularity and run the EESSI client container. And so basically we have a container that has EESSI available inside. that should work on any Linux, and then EESSI should work on, the container should work on EESSI should work on any Linux distribution then. So as long as you have Intel, AMD, or ARM CPUs there, it should work. There's detailed instructions available at that web link, which we can also put into the notes as well to make it available to you. And that gives you the specific command that you need to start that EESSI environment inside a container. Okay, so how exactly does all of this work? So we go back to this picture again that I explained before about how we have the different layers of EESSI, but I want to explain each of those layers one by one to show you what is actually meant when I talk about these layers. So the first one is the distribution layer, so also called our file system layer. So basically we had that CVMFS directory that after we configured CVMFS, this directory automatically appeared on our file system, and it had things inside that looked like they weren't there, but because of something called AutoFS, if we know what we're looking for, they magically appear. And so it's a POSIX file system, and basically the things are there as they appear like they normally do in a POSIX file system. What we use is CVMFS. So this gives us our global distribution of software installations. CVMFS is around quite a while, and it's used, as you might have guessed, by CERN. And they use that to distribute software and have done for quite a long time, to distribute software that's used to analyze data coming from the experiments that are done at CERN. So this is a method that gives you a way to centrally manage software stacks, and that's why we're using it. The way it's done is through a network of mirrors. So basically you have the main copy of the data and the software in what's called stratum 0. And then you have mirrors of that data in different locations. So these are called stratum 1s. And so there's a complete copy. Each of these stratum 1s has a complete copy of the data that's stored in stratum 0. And they make that available then through a SQUID proxy. So the clients then connect to the stratum 1s. They can also connect through something called a SQUID4 proxy. So basically you can have different levels of, with CVMFS, you have different levels of caching, right? So you have a complete copy, say, in the stratum 1. You can have a partial copy in the SQUID4 proxy. So the things that you're most interested in, or your site is most interested in, are stored in the SQUID proxy. So you might put something like that in front of a cluster, or even a system inside your cluster. If you're using a lot of what's available inside EESSI, you might even consider having your own private stratum 1. And what stratum 1 you actually use is part of the EESSI configuration repository, or you can configure that yourself. So if you have a private stratum 1 server that you use, you can configure your cluster to automatically talk only to that private stratum 1 server, or to that, or still use other stratum 1s as a backup in case something happens with that your private stratum 1. So this gives us multiple levels of caching. So that's outside of the system, but also inside the system, we have multiple levels of caching as well. What that means in the end is that we get that same software stack available everywhere, because it's HTTP based. Any client can talk to these stratum 1s or these SQUID proxies over normal HTTP traffic, right? So we can get the same software stack available everywhere, regardless of whether it's our own laptop, it's a virtual machine inside my laptop, it's an HPC cluster, or perhaps it's in cloud, as we've seen before. For the compatibility layer, you have, what we use is Gen2 prefix. What is Gen2 prefix? Is basically an operating system in an unusual location, right? So that's the prefix part of the name. So we put Gen2, we put our operating system, but put it into a non-standard prefix, okay? In our case, we're putting that prefix inside of CVMFS, and that's how we ensure that that compatibility layer is distributed across to all the clients. So basically, we're putting an operating system inside of a file system layer. What that compatibility layer consists of is tools and libraries low level things that we're interested in, that we need. It doesn't include the Linux kernel, and it doesn't include drivers for the hardware that you have in your systems. You could consider it in the same way that you think of a container image, but with the benefit that you don't need a container runtime. And that has a number of significant advantages, right? That it doesn't require runtime for this overlay operating system. The compatibility layer is not performance oriented, right? So it supports families of architectures, not specific architectures. So basically, it supports ARM, x86, and in the future RISC-V, so that we have actually done work to support the compatibility layer on top of RISC-V. We don't ship that support yet because we're still working on it, but we have done that. And we level the ground then, because of the compatibility layer, then we level the ground across client operating systems. So it works on Linux distros, on all the Linux distros that probably most people use, and then also in the future, the plan is also to make that work on Mac OS. So we've done some proof of principle work on Mac OS, but it's not our primary target right now. We're more interested in getting things working for lots of different architectures on HPC systems. So in our production repository right now, we have the two families. So we don't have RISC-V yet, but that's something that we will be working on in the next year or so to get RISC-V support in there. The final layer then is the software layer. And that's the thing that provides the scientific software. So the application, the software we care about performance and all those libraries that those applications might use, and all the dependencies of the applications and libraries. These are optimized for specific microarchitectures. And then, as you've seen during the demo, based on what whether it's ArchSpec or ArchDetect, as it is in our production repository, based on what we detect for your hardware, it will choose a specific subdirectory for the software installations that you want to use, right? So it would choose the right software subtree based on the architecture you have, or the best match, at least, maybe not the right one, but the best match that we have. So giving you the best performing software that we ship. It leverages the libraries that come from the compatibility layer, not from the host operating system. That's what gives us the portability, right? So relying on the host on the compatibility layer means that we should have binaries that are actually work on multiple different systems. The software that we ship in the software layer, that's built with EasyBuild, and then that includes shipping all the environment modules to use the software inside. Our user interface is the environment module tool, and the specific version implementation of that we use is LMOD, and that was what provides us with the user interface. The best subdirectory is automatically selected by ArchSpec, but in the production release that we've just done is actually a bash implementation to just of some of what ArchSpec can do, called ArchDetect, and that's what we're using in production because it's a little bit lighter weight. That's good, but how does it compare to the software stack that is actually available already on HPC systems? So we did this experiment where we looked at quite a large scale, so we did experiments up to 16,000 cores on the USEF system. So that's at Jülich Supercomputing Center. So a Zen 2 system that was available at Jülich Supercomputer. This is from a couple of years ago, but the principle remains the same. We did 3 different measurements here. So we did the EESSI stack with Zen 2 support. We also looked at what would happen if we had run just the generic binaries that were compatible with the system, but don't actually use all the features that were available to us with Zen 2. So that's the black one is EESSI, and the blue one is EESSI, but with the generic binaries. And then we compare that to the same software package, not built in exactly the same way, pretty close, but not exactly the same. But it was the same version of the software package, right? The same version of GROMACS that we're comparing here. So it's the same version of GROMACS, just built in slightly different ways. And we can see basically that, and this is perfect scaling. So the line that goes up here is perfect scaling. We obviously lose that perfect scaling after some months' time. that's not important. What's important here is that the performance of the EC stack is the same or very, very comparable, and in some cases, as we get later on, even better than the host software stack. So that was just a proof of principle that just because we ship something that's can be built, can be run in lots of different locations, doesn't mean that we're sacrificing performance. And we can see again, as we might expect, is that when we use generic binaries, there's a big drop in performance, right? So that's just a reproduction of something that we already probably knew. This comes from a paper that we released, and the link to that paper is available on the slide if you'd like to take it. It's quite a long paper, but perhaps worth a read. So what's the current status of EESSI right now? The production repository has been released in the last couple of weeks. We have lots of, so what the scripts and playbooks and the documentation and everything that we use to make EESSI available and usable, that's available under the EESSI GitHub organization, right? So on github.com. We provide the Stratum 0 is at the University of Groningen. And then for the production repository, we currently have 2 Stratum 1 servers, one in Europe and one in the US. But we will probably add more layers of Stratum 1 servers in the coming weeks. But those are backed by cloud providers, should be very reliable. The software that we have currently only CPU only, and this is actually, list comes from the pilot stack, but what we're actually shipping in the production repository right now does include TensorFlow, and a lot of the other packages are in the works, so should appear in the very, very near future. And the hardware targets that are supported, well, we have those families, right? So we have ARM and x86, so we have generic binaries that are available there that should work with hardware going back 15 to 20 years probably. And then we also have specific versions of Intel, AMD, and ARM chips, right? So which should support even the most modern versions of those chips that are available. So, for example, the ARM software that we have, which is Neoverse N1 and Neoverse V1, that would support will be the design of Jupyter, so the first exascale system in Europe that's available next year. So that's the same instruction sets that will be used on Jupyter at Jülich Supercomputing Center. We have NVIDIA GPU support that has been verified to work, at least initially anyway, and will be available in pilot mode or in kind of, a first release of that GPU support will be available before the end of the year. That's currently under code review, so we expect that to be released soon. We've had a lot of support from cloud providers, so Azure and AWS in particular, and they've sponsored credits for us to allow us to develop all the infrastructure that we need and to keep providing EESSI as a service as well. So we thank them very much for that. Now, the question that came up in Slack already is, what about adding the software that I care about and shipping that with the EESSI production repository? So what does that process look like? So you have a software package and you would like to ship that software package with EESSI. In the best case scenario, you basically just make a pull request to the EESSI software layer. And that's a repository whose home is on GitHub. And that pull request then is reviewed. And then when the reviewers review that pull request, then they will trigger a bot. So kind of an application that we have running somewhere that will go away and submit a lot of build jobs for the software package that you want to include on all of the architectures that we have available to us, right? And that the building of that software, it uses EasyBuild underneath. So basically, you need a recipe that's compatible with EasyBuild to be able to do this, and it should be contributed to EasyBuild as well. But basically, when that's done, then we can build all that software. EasyBuild already has testing inside, so you can already run the unit test for software packages and things like that. But especially for marquee tests, for marquee packages, so like for big important application software, we also want to do testing with Reframe. So Reframe is a tool that you can use to do standard testing, right? To do correctness tests. but also you can use it to do performance and scalability tests as well. And that's something that we're interested in. So when we ship large scale applications, we expect them to work at scale. And we want to be able to check that they do. So part of what we want to do is ship tests for applications where we can check that performance and that scalability and record that the performance and scalability over time. Once that testing has come back and has passed, then we can basically create tarballs of those software installations, and then they're placed in something called S3. It's just a storage backend that you find a lot in, say, cloud providers. So they're placed in these software installations are placed in a special location. Oops, sorry. And then there's a cron job that recognizes that these tarballs have been placed there, and it checks to see if these tarballs can be unpacked into the Stratum 0 server of CVMFS. And if that's the case, then it opens a pull request to another repository called the staging repository of EESSI, where again, somebody has to make the review to make sure that what is being touched by those installations is only what we expect to be touched by the installations. So we have a review to make sure that the installations are not touching unexpected files. And then once that's approved by the reviewers, then it'll get automatically deployed into the EESSI repository and be available anywhere where EESSI is available. Recently, I've been calling this kind of like passive continuous distribution, in the sense that once it's available in EESSI, it will automatically be available anywhere where EESSI is available. That includes, for example, inside a container. So the EESSI container is basically automatically updated without touching the container itself. And because we're constantly making new software available via the CVMFS repositories. So that's what adding software, excuse me. That's what adding software to EESSI looks like. What kind of use cases does this enable for us? So in our paper, we talked about some of these use cases, but I actually want to go through some of them in the tutorial today as well. So, well, the one that we've talked about so far is that you have this uniform software stack, right, that you can use on different environments. So you can have it on your laptop, you can have it on servers in the cloud and on the clusters. And once you start thinking about you having that software stack available, it also means that you can have portable workflows, right? So you can have, if you have lots of different packages that you want to use in a workflow, you can couple them all together. And if they're all available in EESSI, it means that you also have a portable workflow. So you can easily move your workflow between different architectures, for example, or different HPC systems. Continuous integration is just a particular type of a workflow, but it means that EESSI can be used in those integration environments as well. So we already, for example, have an EESSI GitHub action that I'll talk about a little bit later. But basically, because you have so much software and dependencies and compilers and MPI runtimes and math libraries available within EESSI, you can leverage all those in your continuous integration environment. So you don't have to maintain, like a lot of people might maintain a container image or something like that provides this kind of software, but with EESSI, you would no longer need to do that if you were relying on EESSI to deliver your compilers and all your dependencies. This also significantly facilitates setting up infrastructure for HPC training. So typically with HPC training, you need that like a user environment for people to use, and sometimes that can be difficult to get. You can have a lot of hoops that you have to jump through, to do training for HPC systems. And then the other one is then that it also enables a lot of collaboration that we can do with software developers and also with application experts, right? So we ship things to the best of our ability, but obviously, ultimately, to ensure we have the best performing software, we're relying on contributions from other people. So that might be the application users, so people who are experts in using a certain application, and they might be able to help us improve the way we ship a certain software package. And obviously, if we work together with developers, we can do our best to make sure that we're shipping the best possible version of their software package. All of these, again, are discussed in that open access paper. So the uniform software stack, we've kind of gone through this, but I'll say it again. We have that same software everywhere. We have all those different CPU architectures that are supported. We can basically use any Linux distribution because we're only really relying on the kernel that comes from that distribution. That includes then the Windows subsystem for Linux, and potentially could include in the future Mac OS. We have support for high-speed interconnects, and the way we build our Open MPI or our MPI layer, we ship it very fast, which means we already have support for almost all of the typical interconnects that you get out there. So including things like InfiniBand, but also the unusual interconnects like EFA, for example, in AWS. There's a special fast interconnect there called EFA that you can use, and that's already supported inside EESSI. We can also support GPUs. So we've done the work to support NVIDIA GPUs, and the next thing that we will look at is doing the same thing for AMD accelerators and other accelerators going forward in the future as well. What we do not do is compromise on the performance, right? That's a principle that we have. So we give you optimized installations for the stuff that for the CPU that you have access to, and we auto detect that CPU for you. And this is obviously in large contrast to other portability solutions, which might be like generic binaries and things stuff like that is used in, for example, containers. And of course, we facilitate this migration from laptop to HPC. We also facilitate cloud bursting. So obviously, if you are using the EESSI, it's straightforward for you to use EESSI also in cloud environments as well. We don't solve getting your data to those cloud environments, but we do solve making sure that the software that you're accustomed to is available in that environment. EESSI also, as I said, EESSI supports portable workflows, so they're going to be a lot easier if you are relying on EESSI, because we are taking care of that portability solution for you. And workflows typically involve using a lot of different tools, and they all need to be available in all the locations where you want to use their workflows. We can actually ship those workflow definitions as well, so you can use tools like SnakeMake, Nextflow, or other workflow tools. On top of EESSI, we can ship SnakeMake and Nextflow within EESSI and the other tools as well. And the actual workflow definition could potentially be shipped inside EESSI as well. So if you actually can define your workflow in these environments, so using these tools, we could potentially ship those in EESSI as well. Another thing that you can do is actually ship your execution environment inside your Git repository. So if you use a tool called direnv, what direnv is basically a tool that allows you, once you enter a certain directory, it does things to your environment, right? So you get a particular environment once you enter inside a particular directory. And actually, we're going to give that a try now. So if your users have, if the people who are cloning your Git repository have EESSI available and have the direnv tool available, they can actually start running your workflow straight away after cloning, right? And we're going to give that a try now. All right, so this is our second hands-on. We're going to we're shipping a workflow with using EESSI. So the scenario is, again, that we're on this cluster that I've made available for today. EESSI is already available there, and you've already used it, but direnv is not. So what we're going to do is we're going to clone a workflow that leverages EESSI. So another example workflow. Again, the repository that you need to clone here, full command is available there in the notes. The workflow is really trivial. You can have a look at it inside once you've cloned that repository. And what you're going to do is you're going to enter that the cloned repository. You're going to source a particular file, and that's actually going to install direnv for you. So like I said, direnv is not already available on the system, so you'll need to install direnv. And you need to allow, direnv in the directory. Well, we'll see that in a second. So direnv will tell you that it's not allowed to run in a particular directory, and then you need to tell it that it's okay, it can run in that directory. And so you need to give it explicit permission to run. And then once you do that, you'll see some output, and then you'll be able to run that workflow straight away. I'll leave this slide up for a minute so you can read over those commands and maybe start doing things for yourself, and then I'll actually do the work. I'll do the hands-on as well myself in a minute. But I'll give you a couple of minutes. just to try this out on your own.
We are getting lots of very good questions in the EESSI Slack, by the way. So thank you very much for that. We're doing what we can to keep up, but do keep them coming.
So hopefully all the commands you need have already been moved over to the notes. So I might do the actual hands-on myself as well, just to give me something to do while you guys are busy as well. So I'll start a new shell. Oh, I have a new shell already. The repository that I need is this one. I actually already have a clone, so let's do it. Yeah, it's already here. So we go into EESSI explore example. Oops, sorry. You can see, oh, I've already run this workflow, but I cleaned these out. So there's a couple of some stuff related to Nextflow already here. You can see there's a hidden file called installer dirend, and I can source that file already. So .install dirend. Yeah, let's have a look at it first, actually. So I didn't make this visible because I don't really like what it does. I think it's a little bit invasive, but for the purposes of the tutorial, it's fine. So it's just going to make a location in our home directory that's actually already available in our path. So stuff we put inside this bin directory will appear in our path already. And it pulls down basically an installer script for dirend from their website and runs that through bash. So basically dirend is written in Go, and so you can easily pull down an executable that will run in your system, and then it's injecting something into your bash RC. So that's the hook basically that makes dirend work with your bash environment. So we can source that script, and when I do, stuff happens. I've already, so when you do this, it would have said that it would have asked for permission, but actually I've already given it that permission already. I forgot about that. So basically it means that it would immediately start loading the environment that it's found in the .envarc file. Let's have a look at what that .envarc file looks like. .envarc. So basically it just has a purge, or it's sourcing the production repository from EESSI. And then it's making sure there's no modules loaded right now. It's going to load the Nextflow module because it needs to run the Nextflow workflow. And it's also going to load a TensorFlow module. We can have a look at what the actual workflow is. So it's just a Nextflow script. I'm not an expert in Nextflow, and maybe some of you have used it before, but basically all the script is doing is giving a couple of different parameters to the say hello function, and running that so with different arguments. And then the last job that it has is to run to just print out the version of TensorFlow and tell me and show me what that is. Right, so that's all I'm doing is importing the TensorFlow module and just printing out the version. And we can run that already. So we can, let's have a look, but it's an executable script. So we can already run the Nextflow script. And everything we need is available to us because of the envarc file. So the Nextflow script starts running. And that's it. It ran really quickly because we have this squid proxy already on the cluster. So a few of you have probably already tried to run this. So lots of the software is already available. And so it runs really quickly. It prints the hello world in all those 4 different languages, and then it prints that version of TensorFlow like we asked it to. So there's a question in the tutorial for this demo situation. What's their end adding here? Maybe not much. So you don't need to do that. But what it does is it means that when you enter, so once you've cloned this repository, and if you have these tools available, once you enter the directory, you can give somebody who's cloning your repository the environment that they need to run your workflow straight away. They do not need to do anything extra. So for example, if I now move out of this directory, it says it's unloaded my environment, right? So I've gotten back to the original environment here. So if I do a module avail, there's nothing available. But if I go into this directory, lots of things happen. And if I do module avail again, you can see I have I would have thought that would have. Let me see if the script works. Oh, sorry, my module environment. Oh, that should have worked. Oh, well, let's try and run the script and see what happens.
There was a related question in Zoom, Alan. Is the changes that DRM does reversible? It seems like it is, because if you jump out of that directory,
yeah, if you jump out of directory,
puts things back to normal. Yeah. So it remembers what it changed, and it can reverse those changes.
Yeah. That's interesting. The behavior of their end has changed a little bit. Before I think you would have been able to see all the different modules that are available here. I'm a bit surprised by this. Or why, I'm not sure why it's not available. It's actually in my module. It's probably something to do with the. Let's try this.
It's probably your
ignore the cache.
Your Elmod cache, yeah. So that's a side effect of Elmod.
And what's the right command here?
Do export Elmod _ ignore cache = 1, and then run module AV. So to be clear, this cache is something very specific to Elmod. It has nothing to do with EESSI. So when, yeah, like this, yeah. Without the.
No.
Huh. That's
anyway,
interesting.
I'm not sure. I have to admit the debugging. That's not the behavior I've seen in the past, and it shouldn't work like that. I'm curious if I have the right. Yeah, okay. So it's not Elmod. That's my problem. Not sure why that's true. Interesting. Anyway, that shouldn't.
Try starting a bash login shell, Alan, and see if you get Elmod then. So bash -L. Now do module -- version.
Yeah.
Yeah. So that's why
that works. Yeah. Okay. Interesting. Maybe some more things to document in this, but basically that's the idea, at least anyway, right? That you can ship the environment that you need to run your workflow inside a file that you can ship with your repository, right? So that means that if somebody clones your repository, they can immediately start using your workflow. Everything that they need to do that is inside the repository. So, I mean, the issue about sourcing EESSI, that's something that we plan on working on soon. So right now, you're sourcing a certain location to make EESSI available. And that's kind of a non-reversible way of accessing EESSI. And obviously, we're very well aware that there is a tool that is reversible, and that's the module environment tool. So what we plan on doing is making it more straightforward to actually have EESSI as a module itself, and that you would load the EESSI environment via a module file. And that, of course, would mean that switching between different releases of EESSI. So, for example, we have, say, the 2023.06 or different versions of EESSI. That would make that more feasible, right? So that's something that we're already working on right now. So I'd give just 2 more minutes to do that, and then I'll continue with the rest of the presentation. Okay. So the next thing I want to discuss briefly is how you can leverage EESSI in a continuous integration environment. So hopefully a lot of you, if you're developing software, are using continuous integration already. And maybe you've heard of things like Jenkins or GitHub Actions or GitLab runners or things like that, right, to help you with continuous integration. What can EESSI do for you? Well, it can provide you with compilers and different compilers so that you can test your software with different compilers. It can give you the dependencies that you need to build your application. And it can provide additional tools like reframe or performance analysis tools that you might need during your development workflows. And the nice thing is that other than CVMFS, you don't actually need any additional software. Everything that you need is going to be pulled in on demand by CVMFS. And typically, when you're building something, you don't use all of the things that are shipped with something like a compiler or any of your dependencies. You're only accessing a small subset of the files that are required, which means that even for applications that seem quite large, something like OpenFOAM, actually on your system, you're really only using a certain number of files and they can be pulled in really quickly. So that's another benefit that you might have over, say, something like a container, which requires you to ship the entire installation. You wouldn't need to do that. You don't need to do that with CVMFS. And of course, then it significantly facilitates running CI tests in other contexts, right? So yeah, you might have your CI environment that you use like GitHub or GitLab or something like that. But you can also you should be able to run those same CI tests pretty easily on your laptop or on an HPC resource or on whatever facility you have access to. So we've even made an EESSI GitHub action available that can do that for you, or it can help you, that's configured to allow you to do that. And so that is providing, like we've just seen, it provides EESSI, but it also provides this DRM tool so you can ship the environment that you want inside that repository, your software repository. You can see that, oh, that's actually, there's a typo there. Let's fix that while I'm here. EESSI. You can see that in action already in the repository connected to this tool, and so I use that in the continuous integration for the GitHub action itself. And then you can see some usage. Actually, this is actually out of date. There should be TensorFlow. It's TensorFlow usage. I'll update it as well after the presentation. But basically, the workflow for TensorFlow looks like this. And basically, we give it some kind of a name, and you say that when somebody pushes to a branch or makes a pull request, that we run some things, right? So say like a build job, we call it, give it a name, we call it a build job. It runs on this operating system. In this case, it's Ubuntu. And you need to check out the repository. So you'll need this other action that does the checkout for you. And then you can use the EESSI GitHub action. That's version 3 that was just released last week. And then you can say what version of the EESSI stack you want to use. By default, it will be the only one that's available right now, 2023-06. But in the future, there will be more. The expectation is that there will be multiple versions of the EESSI stack available. And then if you want to run a test, then basically you just need to run, you need to use a bash environment because of how we make sure that the modules and DRM work in your environment. You need to use bash. But then you just run, you'll already have the EESSI environment available, so you can already run things like module load, whatever it is. So in this case, it's TensorFlow, and then you can run things based on that. So this module load might include, say, like if your application uses CMake, it would include loading CMake, and you might want compilers, you might want NPI runtime, you may want HDF5, you may want other dependencies as well. So you would have all these load statements. You could put them inside the .env file, or you can have them explicitly here in your workflow as well. That's up to you. And then you can build your application however you want to do that as well. So that will be part of the script. But basically, that's how it would look like. And if you run it, this is an old example, which is again based on GROMACS, just so you can see some text that's related to the application itself. If I run the TensorFlow test, which is just printing the version, it's a little bit more boring. This was from, but basically that's what it would look like. You basically, it works is the answer. Basically, it looks like what you would do if you're running the commands locally as well, and they'll be available to you within the GitHub action. The other thing that it facilitates is HPC training. So EESSI can potentially significantly reduce the effort that is required to set up infrastructure for training, especially when we think about things like introductory training or software-specific training, or there are probably other examples you could think of as well. Because typically when you want to do a training, it's with a certain system in mind, but also for many HPC sites, that's their production system, right? So there are scientists who are using that, and typically training may involve creating a reservation on a system. And then you have lots of security concerns, right? If you're talking about doing, say large-scale training, that's not something that you necessarily want to do. So you can cut through a lot of this overhead with EESSI, and then if you couple it with something that can create a throwaway cluster for you. So the one that we used for the cluster today is a tool called Magic Castle. So it generates that throwaway Slurm cluster for you. And Magic Castle supports EESSI already, and also the Compute Canada software stack, which is, I mean, I didn't say it, but I should have said it, is that a lot of the ideas for EESSI, those ideas come from Compute Canada, which is now called the Data Alliance I'm not sure. It's the Alliance, it's the short name, and then there's a long name as well, which I can't remember what it is right now.
The Digital Alliance, Research Alliance, whatever.
Yeah. And so basically Magic Castle as a tool also comes from them. But the ideas, a lot of the ideas behind EESSI also originate from the Alliance as well. So we use Magic Castle today. Creating a cluster was basically just editing a single file. It automatically configured and made that cluster available within about 20 minutes. Magic Castle supports GPUs, NVIDIA GPUs, and also supports fast interconnects as well. So we have tested Magic Castle with InfiniBand that you can find on Azure, and with this EFA fabric that you can find in AWS as well, and it works and shown to scale. EESSI project is actually using Magic Castle for a couple of different use cases, not just for training, but also that's what's behind the scenes with our build and deploy bot as well. That's where we actually run the jobs that are building for all the different architectures. And so we're finding all those architectures on our cloud providers, so on Azure and AWS. There are also commercial alternatives that gives you these kind of throwaway clusters. And they either can do or will support EESSI as well. So in particular with our sponsors, we're working on that. And so EESSI can provide that scientific software that you require for the training. And the really nice thing about that is it means that the attendees can get that same software environment later on their own. So whether it's on their laptop or whether it's on their own HPC system that they have access to, and they can do that tutorial or follow that tutorial or run that tutorial on other resources they have access to because the tutorial was delivered by using the EESSI environment. The last thing I wanted to mention was collaboration with software developers and application experts. So because we have this central software stack, it opens up new doors that weren't really there before, because we can work now. I mean, if developers start using EESSI as a means for them to distribute their application, we can work with those developers directly and with application experts who care about the performance of those applications to verify the installations that we're shipping. So we can check and make sure it's configured and built the way that it should be, that it functions the way that it should, and for different use cases. So typically, you want to make sure, typically there's a lot of capabilities in scientific software. And the typical use cases that are provided for benchmarking purposes are only a small component of what software packages are able to do, right? So we can go beyond that and make sure the software is functional for a lot of different use cases and also performant for those different use cases as well. So this is something we could investigate further. And then these developers could show us and help us develop tests, right? To do extensive testing of their software packages, which we would do via Reframe. And so we could ship those tests as well. And then we can evaluate the performance of the software and enable in general performance monitoring. So say like on an important system, so for example, the Euro HPC system, we could regularly monitor the performance of software applications on those systems. And, you know, in the future, we can think of like something like a stamp that we can give to applications saying that the versions that we ship have somehow been approved by the developers. And that would be a good thing to have, like for major applications that we ship inside EESSI, and so that people are aware that these are somehow been evaluated and approved by the developers. And hopefully, what this might do is relieve software developers from some of the burden of getting their software installed by their user communities. So hopefully, it might facilitate and make that an awful lot easier for them. And maybe removing the need to provide pre-built binary packages or containers or whatever that might be, or lots and lots of support to help people use their software in different environments. And developers can also actually, so as we've seen, developers could leverage EESSI themselves. So whether it's for their dependencies or in their CI environments or however else they might want to do that. So big question, who actually is paying for all this? So maybe hopefully by now you might think that EESSI is pretty good service, but how is it funded and who's paying for this? So right now, the primary source of the funds that are supporting EESSI are coming from Center of Excellence, multi-scale. That's a Euro HPC Center of Excellence, so it's Euro HPC project. It's a 4-year project that started almost exactly a year ago, or this year basically. So it's been on the run for 11 months now. The budget there is about 6 million euros. 50% of that money comes from the EU, and 50% comes from national funding from the partners. And roughly 50% of that 6 million is for EESSI related activities. So that includes like the services that we offer, but also support infrastructures as well. So we do offer support in EESSI as well right now, primarily aimed at the communities connected to multi-scale, but obviously we're aiming to support a much wider range of software than just that for the multi-scale community. Multi-scale is a collaboration between EESSI and CCAM. So CCAM is a 50-year-old scientific network, has a nodal structure, and it's been around for a long time. It's about advanced computational techniques and implementing and leveraging those advanced computational techniques to do important scientific problems, to solve important scientific problems. So EESSI is primarily addressing kind of technical aspects that are related to that effort. And then CCAM is providing all the scientific expertise. The scientific targets of that project are it's all about multi-scale. Maybe that was given away by the name. And there are 3 key use cases. So one of them is helicopter design and certification. So helicopters are pretty difficult objects to simulate, and because they have lots of complexity, lots of large moving parts. You need different scales to do that at sufficient resolution. And certification is actually quite a complex thing for these, because you need those simulations to be able to get the certification. So we're interested in scaling up and in speeding up the certification process for these, and also enabling better simulation of helicopters in general. And another use case is battery applications for sustainable energy. And one of the battery applications we're specifically interested in is supercapacitors. So supercapacitors already appear, say, in high-performance cars. So you have them in some of the Lamborghinis, the latest Lamborghinis. They use them for acceleration. But basically, the supercapacitors are an interesting way to store and release large amounts of energy very quickly. Why are we interested in them? Well, one of the reasons is the applications of supercapacitors is very interesting when you think about the regenerative braking. So especially for large objects. So think about like buses or trams or even trains. And when those kind of objects break, they generate a lot of energy very quickly. Supercapacitors are quite a good way of storing that energy and releasing it really quickly. So accelerating those objects from standing start as well can be very good for that. The other one we're interested in is ultrasound. So you probably know of ultrasound as for diagnostics, right? So as a way of doing diagnostics, because it's non-invasive, which is very convenient. And we're interested in making a digital twin of the ultrasound process to improve the diagnostic capacity of ultrasound, because we can tweak parameters when we have a twin. So we can do optimization there to improve this diagnostics. But also recently, ultrasound has also been considered for its ability to actually as a treatment, right? So in the case of treatment, being able to tune the process is very interesting as well, right? So that's why we're moving towards creating a digital twin for the ultrasound process as well. And the website for multi-scale is there at the end. And so with that, with probably plenty of time left for questions and to open the floor, I leave you with lots of links related to how to get in touch and stay in touch with EESSI environment and all the people who are connected to EESSI. There's lots of links there and there in the presentation, which are available to you. There is a feedback request that I'd like to make. So it would be important to get your feedback to see what you thought of the tutorial today. And I do want to leave plenty of time now so we can have an open discussion. So the recording of this tutorial will end up on YouTube in the end. But I am going to stop if anyone wants to say, ask a question that will appear in the recording, you can do that now. But in a minute or so, I'll switch off the recording, and so we can just talk openly and freely among ourselves about what you've seen and any other questions that you might have. So if anyone wants to raise their hand now to discuss something on that will be in the recording, you're free to do that.
And of course, we're happy to still take questions via the Slack channel as well, which will stay there after the tutorial. So if you're watching the recording, you can definitely still join the Slack channel as well and ask questions there anytime. Basically, we will be around. But we do have time for questions here in Zoom as well. We got a lot of very good questions already, Alan, in Slack, which I think we've been managing well, throwing links around and giving clear answers to people. So
Okay, so I'm going to stop the recording now, and then
maybe before you do, there's one that I would like to mention here. Somebody asked, EasyBuild currently has support for over 3,000 different software packages to install. There's currently about 100 in Easy, at least in the software.easy.io repository. So more binaries when was the question? Well, soon. So we're working on this. Our goal is essentially to have everything that's supported in EasyBuild and that we can redistribute to have that installed in Easy. So literally thousands of different software packages without versions. That should definitely be possible. And the main limiting factor there is two things. We often, when we install something in Easy, we may run into trouble when making sure it only uses stuff from the compatibility layer. So that's a limiting factor. If we want to make sure it works everywhere, it can only use stuff from the compat layer. So that we need to make very sure of, that it's not picking up something from the build host operating system. And another issue we often see currently is that we're trying to install things that work both for x86 and ARM. And the ARM is getting better, but every now and then we still run into surprises there. And we always try to fix that installation first on ARM before we throw the towel and say, okay, this is only going to work on x86. So very often with a small patch or with a little bit of extra effort, we can get it to work on ARM, and then we do before we include it in the repository. But the longer term goal, weeks, months, is definitely to get as much as possible that is supported in EasyBuild also installed into Easy. And then from there, the sky is the limit.
Yeah, just to mention on that one, that obviously the license matters, right?